Okay, so what if I told you there's a technology on the horizon that sounds like it's straight out of science fiction, but is actually becoming a reality right now? We're talking about a completely new way of computing, one that could solve problems we used to think were, well, impossible. Today, we're diving into the pretty wild world of quantum computing. Think about the absolute biggest challenges we face, like discovering life saving medicines, or untangling global logistics, or even building a truly advanced AI. These are what folks in the field call intractable problems. Basically, they have so many moving parts that even our absolute best supercomputers would take literally thousands of years to figure them out.
So, how in the world do you tackle something like that? Well, with a leap in power so big, it's kind of hard to wrap your head around. Get this, a recent quantum computer took on a problem that would have taken the world's fastest supercomputer ages to solve, and it did it 158 million times faster. It finished in just a couple of minutes. That is the kind of game-changing power we're talking about.
To really get why this is such a monumental leap, we first got to talk about the limits of the computers we use every single day, right? From the phone in your pocket to the biggest data centers, all classical computers work sequentially. They do one thing at a time, in order. And that's great for most stuff, but for those super complex problems, it just creates a massive bottleneck. The whole difference really comes down to one thing, the fundamental building block. A classical computer uses bits. Think of them like a simple light switch. They are either on or off, a 1 or a 0. But a quantum computer, it uses something called a qubit. And here is where things get really weird. A qubit can be a 0, it can be a 1, or believe it or not, it can be both at the exact same time. And that one tiny difference, well, it changes absolutely everything. So, how is that both at once magic even possible? Well, it all comes down to the bizarre, kind of counterintuitive rules of quantum physics. There are two big ideas in particular that give quantum computers their incredible power: superposition and entanglement.
First up, we've got superposition. The easiest way to think about a qubit in superposition is to picture a spinning coin. While it's spinning in the air, it's not really heads and it's not really tails. It's kind of both possibilities at once. It's only when you measure it, when you catch the coin, that it collapses into one definite state, either heads or tails. This is the both-at-once superpower that makes quantum computing tick.
Here's a pretty good analogy for it. Because a classical computer processes everything one step at a time, it's kind of like a trumpet. Sure, it can play a beautiful melody, but it's always limited to playing one single note at a time. But a quantum computer, because of superposition, is way more like a piano. It can play all the notes at once to create a rich, complex chord. It's exploring tons of different possibilities, all those notes, all at the exact same time. But superposition is really only half the story. The other key ingredient is something so strange that Albert Einstein himself famously called it spooky action at a distance. He was talking, of course, about entanglement. Entanglement is this deep, almost mysterious connection between two or more qubits. Once they're linked up, they act like a single system. So if you measure the state of one qubit, you instantly know the state of its entangled partner, even if that partner is on the other side of the planet. It's this property that lets them all work together in perfect harmony. Let's try another analogy, because this gets weird. Imagine you have two magic dice that are linked together. You roll them, but to keep them covered. You give one to a friend, and they fly to the other side of the world. The absolute instant you lift your cup and see you rolled a 6, you know with 100% certainty that your friend's die is also a 6. It's like they have a shared fate, no matter how far apart they are. Okay, so let's recap. We've got superposition, which lets qubits explore tons of states at once, and we've got entanglement, which links them all together so they can work as a team. When you combine those two crazy quantum ideas, you unlock a fundamentally new kind of power. So let's just put it all side by side to make it super clear. Where classical computing is sequential, quantum is parallel. Where a classical computer gives you one definite answer, a quantum one gives you probabilities. It points you toward the most likely right answer. And yeah, it's really important to mention that for now, the error rate is still pretty high. This technology is powerful, but it's also incredibly delicate. Maybe the best analogy for what this all means in the real world is that classic needle and a haystack problem. A classical computer, it has to check one single straw at a time. A quantum computer, using superposition and entanglement, can basically look at the entire haystack all at once and tell you where the needle is most likely to be. So, what does being able to check the whole haystack at once actually get us? Well, it means we can finally go back to those giant, intractable problems we talked about at the beginning, because now we might just have a tool powerful enough to solve them. And the potential applications here are just staggering. I mean, we're talking about simulating molecules to design brand new drugs and materials with pinpoint accuracy. We're talking about revolutionizing AI, allowing machines to learn from way more complex data. And get this, creating new, unbreakable codes, while also having the power to crack our current ones. This isn't just a small step up, it's a total paradigm shift. Now, this all sounds incredibly exciting, and it is. But it's also important we ground ourselves in reality here. This technology is amazing, for sure, but it is still very, very new. We are really at the very dawn of a whole new era of computing. Right now, we're in what scientists call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Noisy basically just means the qubits are super sensitive to their environment, like even a little bit of heat or vibration can cause errors. And intermediate scale means we're still working on building machines that have more and more of these stable qubits. And let's be super clear about something. Quantum computers are specialized tools for very specialized problems. So, no, they are not going to be replacing your laptop for writing emails or watching videos anytime soon. Don't worry. Our classical computers are, and will continue to be, fantastic at all those everyday things. Just think of quantum computers as this amazing new tool for a very specific and very hard set of jobs. You know, when you really get down to it, the ultimate promise of this revolution isn't just about getting faster answers to the questions we already have. No, the truly transformative part, the really exciting thing, lies in all the new questions it's going to let us ask. Questions about the universe, about biology, about intelligence itself. That, for the very first time in human history, might finally be within our reach.